Hi everyone, my name is Sujit Kachitri, and today I'll be talking about quality inference from living digital twins in IoT-enabled manufacturing systems, also abbreviated as QUILT, like a digital fabric covering various physical aspects of manufacturing systems. The other authors of this work are Sina Faizi, Archimedes Canito, and Mohammad Abdullah Al-Farouk. The content of this presentation are as follows. First of all, I'll be going through the introduction section. Then I'll go through the background work, then I'll present the methodologies for building the digital twin, then I'll go through the experimental and results section before finally concluding the presentation. The real-time digital representation of the physical domain is known as the digital twin. It can also be defined as an integrated multi-physics, multi-scale, probabilistic simulation of a complex product which uses the best available physical models, sensor updates, etc. to mirror the life of its corresponding twin. Digital twin can acquire and consist of large historical context, performance data, computer-aided design models, finite element analysis models, operational history, maintenance data, etc. from the physical twin of the system. It is expected that the future trend will be in using the capability of Internet of Things and producing massive amount of data to create a digital twin that interacts with the cyber domain. In fact, Gartner predicts that digitalization will be the top trend in coming years, and the digital twin has been placed in the innovation trigger phase of emerging technologies in the hype cycle. Let's talk about various components of the digital twin and what it really consists of. As mentioned earlier, the digital twin acquires various data as input, such as operational, maintenance, environment, etc. Utilizing this data, various models of the systems are created, such as aging, performance, error, etc. The combination of these models is what digital twin consists of in the virtual domain. The main goal or output of the digital twin will be to provide better control, optimization of the parameters in the virtual domain, performance monitoring in the real time, to name few. It will be evaluated based on various key performance indicators such as reliability, quality, etc. One of the major value added by the digital twin will be enabling cognition by providing advanced diagnostics and prognostics capabilities. It will also provide visualization of every state of the physical system in detailed resolution. In terms of manufacturing, the digital twin will consist of a virtual representation of a production system that is able to run on different simulation disciplines that is characterized by the synchronization between the virtual and the real system. For example, if we consider the supply chain of the manufacturing system, in the design phase, the abstract paper concepts, prototype models, wind tunnel for example, may be represented in the virtual domain using computer-aided design tools. In the engineering phase, the various materials required to make the product can be represented by the corresponding computer-aided engineering models of the material, such as finite element analysis models, computational fluid dynamics, etc. Engineering model may be created to represent various manufacturing systems involved and the corresponding process. These models would be able to simulate the production of the products, predict the KPI and the manufacturing system health, represent the status of various components, etc. In the operation phase, the products that have been designed operate in the real world. Hence, various performance model of the product may be used to represent its health. Moreover, since these products will be operating over various locations, various performance model may be sharing information to create a better digital twin model. In the maintenance stage of the product, various maintenance needs of the product may be represented by an aging model of the virtual domain. These interactions happen throughout the supply chain in the manufacturing systems. In this presentation, we focus on the production stage of the supply chain and hence focus on the digital twin of the manufacturing systems. More specifically, we focus on how IoT-enabled devices with lots of sensors will help us in acquiring large amount of data from multiple modalities such as acoustics, vibration, thermal, etc., and help us in building digital twin models in the form of performance, aging, functional, and anomaly models. The digital twin models will also be able to provide feedback to improve the production system. The major research challenges that we consider in this presentation consist of questions such as how to utilize IoT-enabled sensors in building the digital twin of legacy manufacturing systems, what signals to observe, and how to keep these digital twins up to date. There are a large amount of related work in the literature for building the digital twin of the manufacturing systems. However, no work considers utilizing the indirect side channels to build and maintain the digital twins, which is considered in this presentation. Our major contributions are as follows. We provide modeling digital twins using side channels for quality inference and fault localization, and provide a methodology for keeping the digital twins up to date. So far, we have finished the introduction section. Now let's move on to the background section next. Let us go through some of the concept definition to better understand the scope and contribution of this presentation. To do this, I'll present the three stages of manufacturing, that is design, production, and operation. In the design stage, the digital twin of the product is first created using computer-aided design tools. Since this presentation proposes to create a digital twin model of the manufacturing systems, we will focus next in the production stage. In the production stage, the digital twin of product is provided to the manufacturing system. The manufacturing system can be decomposed into cyber and physical components. However, in a manufacturing system, mostly the physical components also interact with the environment, which is represented as E-system. The interaction between the physical component of the manufacturing system and the environment may be stochastic due to unpredictable nature of some of the environmental factors. On the other hand, the product digital twin drives the system physical twin in a deterministic manner. However, the outcome of the interaction between the product digital twin and the system physical twin becomes stochastic due to the influence of the environment. The manufacturing system produces the required product, and the produce goes to the operation phase of the manufacturing supply chain. Coming back to the production phase, while manufacturing the product, various unintended emissions are released from the physical domain of the manufacturing system. These emissions can be monitored by the IoT-enabled sensors, which are used to maintain the digital twin of the system which have been modeled earlier. Now, the product digital twin can integrate the digital twin of the system for various purposes, and the digital twin may in turn control the production system by providing feedback to maintain process quality. In this presentation, we provide two models for representing the digital twin of the manufacturing system. The first model allows designers to localize the fault during the production of product digital twin. While manufacturing it, the emissions observed from the IoT sensors allows the digital twin of the system to analyze if the product being manufactured is faulty. This capability allows automatic inspection of the product being manufactured, which are not visible easily. The second model provided in this presentation utilizes the product digital twin, the environment, and the process parameters to infer the quality of the product physical twin virtually without having to manufacture it. Manufacturing system consists of cyber and physical domain as mentioned earlier. The competing components in the cyber domain have processes that communicate with the physical domain. A cross-domain signal that is passed from the cyber domain to the physical domain have the possibility of impacting the physical domain characteristics. This phenomenon is more prominent in manufacturing systems, where the digital twin of the product causes the physical twin of the system to behave in a certain deterministic manner. However, due to these characteristics, there exist physical emissions which also leak information about the digital twin of the product. We denote these emissions as side channels, as they indirectly reveal the information about the cyber domain interaction due to the particular physical implementation of the system. In manufacturing systems, there can be various kinds of side channels such as electromagnetic emissions, power, vibration, acoustics, etc. The thing is, there are various IoT devices which have all the necessary sensors to capture these emissions from these manufacturing systems. Now we have concluded the background. Next, we'll go into the building digital twin section, where I'll talk in detail about the methodologies incorporated in building the digital twin of the manufacturing systems. In order to build a digital twin, at first, the digital twin of the product is passed to the physical twin of the system. The physical twin of the system is constantly influenced by the environmental parameters, such as humidity, temperature fluctuation, etc., represented by gammas in the slide. When the physical twin of the system is operating, various analog emissions, which are unintended, are being continuously monitored from various side channels. These raw analog emissions are preprocessed and various features in time and frequency domain are extracted, which are synchronized and segmented. To do this, various product digital twin parameters are parsed, which are represented as alphas in the slide. The proposed digital twin of the system consists of 4 blocks. The first one is the clustering algorithm, which clusters the analog emission to create a fingerprint of the alpha parameters. Since we fingerprint the system from the analog emissions, we effectively capture the interaction between the product digital twin, the system physical twin, and the environment. The second model consists of the quality inference model. This model is initially trained using data-driven modeling approach. It utilizes the analog emissions, the process parameters, the product digital twin to infer various key performance indicators such as surface quality, dimension, etc. The clustering algorithm data is passed to a fingerprint generation and anomaly localization block. This block utilizes the various parameters from clustering algorithm and create fingerprint to be stored in the library, and also provide an algorithm to update these fingerprints for updating the digital twin. The digital twin is then utilized to infer various quality parameters and perform runtime localization. The major product digital twin parameters considered in this presentation are GM codes. These codes are the instructions that carries the process and product information. To understand how they are created, we briefly go through the digital process chain of the product digital twin. First of all, the digital twin of the product goes through a computer-aided design tool where stereolithography files, which are 3D coordinates, are created. It then goes through a slicing algorithm which slices this 3D geometry into multiple layers. It then passes through a toolpath generation algorithm which finds the best route to traverse in each layer. The outcome of this toolpath generation algorithm is what is known as G-codes, and combined with the machine-specific codes, it in combination forms GM codes. For generating the fingerprint of the digital twin product from the IIT sensor data, first of all, it is parsed to its corresponding parameters such as alpha 1, alpha 2, etc. The parsed values will depend on the type of manufacturing system. The parsing for an additive manufacturing system, that is the GM codes, will be demonstrated later in the slides. In this paper, various time domain features such as energy entropy, peak-to-peak features, root mean square values, skewness, standard deviation, etc. are considered. In the frequency domain, features such as mean frequency, maiden frequency, short-term Fourier transform, continuous wavelet transform, etc. are considered. All the analog signals are first synchronized by performing up and down sampling and testing the various window size for highest modal accuracy. These features have been selected by calculating the Gini impotence, or mean decrease impurity of well-known time and frequency domain features, used for analysis of the time series data. Principal component analysis is then performed to further reduce the dimension of these features. For generating the fingerprint of the parsed parameters, clustering algorithms is used to generate clusters that group the similar feature into a single cluster. For analyzing the clustering algorithm and the corresponding fitness of the cluster number, the silhouette coefficient is calculated for each sample. It measures the similarity of the feature to its assigned cluster compared to other clusters, with a high value representing its close match to the assigned cluster. Let us assume that we extracted two features each for the product digital twin parameters, the alphas, such as alpha 1, alpha 2, and alpha 3. Then, a silhouette coefficient is calculated among each of these features. Here, A is the average intra-cluster distance, and B is the mean of the nearest cluster distance. The clustering is carried out for each group of the features for all the analog emissions. The cluster centers, the cluster number, and the corresponding average silhouette coefficient of the analog emission is stored in a library, effectively representing the fingerprint for the given parsed digital twin product parameter. The digital twin consists of the cluster parameters, silhouette threshold, group IDs, etc. stored in its fingerprint library. In order to localize the anomaly while producing the object by the manufacturing system, first we extract various features from each of the side channels. Then, based on the groups of the digital twin product parameters, we calculate the deviation of the fingerprint of the features extracted from each of the channel and the groups. If for any of the channel, for each of the group has the silhouette coefficient varying higher than the silhouette score plus the silhouette coefficient threshold, then it is given a Boolean value of 1 for denoting it deviated. The fault or deviation of the features from its original fingerprint in time is mapped to the space utilizing the product digital twin parameters. Since the product digital twin parameters are continuously fed to the manufacturing system, we can correlate the time to the exact digital twin parameter, which in turn will be used to localize the space of the product where the fault occurred. For updating the digital twin model, the library of fingerprint for the digital twin product have to be updated. However, before updating the library, it should be checked if the anomaly in the fingerprint is temporary or it is due to the degradation of the machine over time. In order to update the digital twin, the proposed algorithm in the system digital twin keeps track of all the digital twin product variables that deviated. Then, it will calculate the average deviation of the feature, for instance, of digital twin product which has been passed through the system. This instance can either be just one, which means the check for the digital twin aliveness will be done after producing each object. After calculating the average deviation, it measures if the average deviation is greater than the feature threshold. This feature threshold is assigned for individual feature group. The group deviation for each of the features is added if the deviation is higher than the threshold. Then, average group deviation is calculated based on total number of feature groups. It is then checked if it is greater than group threshold. If it is higher, the channel deviation for each channel is increased. This is continued until we get an average channel deviation threshold. Then, finally, if this is greater than the channel threshold for the deviation, the fingerprints for the digital twins are updated. All the threshold for the digital needs to be carefully selected to reduce the false positives and false negatives for making the decision for updating the cluster, which can be costly otherwise. To infer the quality variation, we estimate a function QD. Specifically, we treat QD as a function of analog emissions, product design parameters, process parameters, and environmental parameters. The quality deviation occurs due to the fact that environment affects the system process parameters. Due to this, when the product is sent to the manufacturing system, variations are introduced in the product. However, when the environment affects the process parameters, it also changes the physical structure of various components such as, for example, creation of rust, mechanical eroding, etc. These changes may cause the side channel analog emissions from the system to vary. The relation between various environmental factors, process parameters, and design parameters may be modeled using first principle or physics-based equations. However, estimating such functions will require rigorous multi-domain analysis of the complex mechanical system and may not reflect variation introduced when the system is operating. Instead, we propose to use a data-driven modeling approach to estimate the function QD. This function is estimated using supervised learning algorithm and is also updated when the digital twin update algorithm reaches a consensus that all the fingerprints are outdated. Next, we move on to the experimental and results section. For analyzing the analog emissions from the side channels, we have selected the Cartesian Fused-Deposition Modeling based 3D printer, or Ultimaker 3. The corresponding sensing devices are as follows. Vibration is measured using additive triple-axis accelerometer. Magnetic field around the system is measured using Honeywell's magnetometer HMC5883L. Acoustic emissions from the system is measured using AT2021 condenser microphone and a contact microphone. Current is measured using a low-range picocurrent clamp. These sensors are placed non-intrusively without hampering the normal operation of the system. In our experiment for demonstrating the applicability of the proposed methodology, we have used the above-mentioned sensors which have similar sensor specification available in IoT devices. One of the challenges in IoT sensor-based information extraction is figuring out non-intrusive positions of the sensors. This task may also be machine-specific. In our experiment, the 3D printer's external surface is considered for non-intrusively placing the sensors. Total of 28 uniform positions are selected. For each position, vibration, acoustic, and magnetic sensors are placed and data is collected for various digital twin product parameters. Then, a gradient boosted random forest is used to create simple classifiers to estimate the accuracy of the model based on various sensor location data. The classification accuracy is used as a metric for determining the placement of the sensors around the 3D printer. The digital twin product parameter is selected for estimating the classifier consists of simple GM code instructions such as presence or absence of stepper motors movement in X, Y, and Z axis respectively. The accuracy score of IoT sensor data is shown in the slide. This score shows which of the sensor positions are capable of better classifying the stepper motor movements. It may be noticed that for different positions, the classification accuracy is different. Moreover, this accuracy results also correlate the mutual information between the various sensor position and the side channel themselves. Based on these values, a single position is selected for each of the sensors. However, since 4 acoustic sensors are used, Positions with tougher classification accuracy are selected for the sensor placements. For testing the accuracy of the digital twin for detecting the anomalous signals that can possibly cause deviation in the quality of the product, specialized test 3D objects, as shown in the presentation, is used. We have simulated the variability of the environment by varying one of the physical twin system parameters such as beta 1, beta 2, etc. In our experiment, we have selected flow rate as one of the beta parameters. Flow rate should be maintained for uniform deposition of the filament while printing in Fused-Deposition Modeling 3D printers. However, due to sudden slippage, faulty filament, etc., the flow of the filament may deviate from its nominal value. The digital twin consists of fingerprints for the optimal flow rate in its library and the corresponding cluster of the individual channels. When the object is printed, the corresponding features are passed to the digital twin and the silhouette coefficient corresponding to the digital twin's product is calculated. For the silhouette deviation threshold, various values have been tested for each of the channels. Corresponding to the varying threshold, the receiver operating characteristic curve for 4 of the side channels is shown in the slide. It can be seen that the area under the curve is higher for the acoustic and vibration data, whereas it is less for magnetic and current data. This tells us that the acoustic and vibration are a good source for localizing the faults for the flow rate variation. The anomaly detection accuracy for each of the sensors is shown in the slide. Corresponding to the RC curve, it can be seen that analog emissions from microphone number 4 are more accurate in detecting the degradation of the flow rate. This is due to the fact that emission is collected by the contact microphone attached near the extruder's taper motor. Moreover, the average accuracy across all the channels in detecting the anomalous flow rate was 83.09%. To check if the digital twin model gets updated to reflect the current status of the system, we performed 2 experiments. In the first experiment, the current digital twin with its fingerprint library is used to predict the class labels, true for update and false for do not update, for the degraded flow rate of 60%. Then, based on its calculation of the average silhouette deviation, the updated digital twin is used to predict the class labels again, for the same degraded flow rate of 60% to see if the digital twin gets updated again. The result of degradation analysis is presented in the slide. It consists of true negative rate, false positive rate, and update decision taken for each channel for the whole cluster. When the system degrades, we expect the digital twin to find higher negative labels being generated as the silhouette score will be lower than the average silhouette score stored for all the channels and group. It can be seen that out of 11 channels, 4 of them had the decision of not updating the cluster, and 7 of them opted for updating the cluster. Hence, the cluster got updated. On the other hand, once the cluster has been updated, the analog emissions are labeled as true. Hence, we expect to see higher true positive rate and lower false negative rate. It can be seen that only 3 of the channels gave the decision for updating the cluster again. However, 8 of them opted for not updating the cluster. This shows that the digital twin is able to update itself during degradation that causes emission in multiple side channels to vary. It may be noted that the side channels gave different decisions for updating the digital twin. Out of them, the acoustic sensors and vibration side channels were mostly able to predict the right decision, whereas the magnetic sensors were mostly wrong in this decision. For checking the accuracy of the digital twin in inferring the deviation of quality, first of all, gradient boosted based ensemble of regressors is used to estimate the function QD for the optimal flow rate range of 80% to 120%. For each flow rate, the 5 test objects with thickness of 4 mm are printed, and for each test object, various segments are created to measure the thickness using the micrometer. Then, all groups of features lying in these segments are assigned a single thickness value. Initially, function QD is estimated using optimal flow rate. Then, it is used to infer the thickness of the 3D object for various feature samples with varying flow rate. The accuracy of the digital twin system quality inference model is measured using mean absolute error value. It can be seen that the product physical twin has various quality based on the varying labels of flow rate. More specifically, with varying flow rate, the thickness of the object also varies. The result of the quality inference is shown in the slide. At first, the mean absolute error value of the inference model trained with optimal flow rate range is measured. It can be seen in the figure that for optimal flow rate ranges, that is between 80 and 120%, the mean absolute error value is around 0.5 mm. Then, at each consecutive step, the flow rate of the physical twin of the system is varied with a step size of plus 10 in the positive direction, and at the same time negative 10% in the negative direction. It may be seen that in both the direction, when the system ages, that is degrades with an increase or decrease in the flow rate, the digital twin of the system has increased mean absolute error without the update. This is intuitive as the digital twin of the system has not been updated to the new fingerprints. However, once it has been updated, the mean absolute error is lower. It may also be noticed that when the system degraded with flow rate at 160% and 50%, the wrong decision was taken in not updating the quality inference model. Due to this, a large increase in mean absolute error was observed for quality prediction. However, this faulty decision was recovered in the consecutive stages. In summary, we have presented a novel methodology for building the digital twin of an additive manufacturing system using indirect side channels. The digital twin models built here are anomaly, localization, and quality inference models. We showed how low-end sensors available in IoT-enabled devices can be utilized to acquire data from various side channels. Moreover, we also presented how the digital twin model can be updated using various side channel information collected from the side channels. Thank you for viewing this presentation. This work was partially supported by the NSF CPS grant CNS 1546993.